Grounding electrode or electrodes are required. A grounding electrode system should be installed for any raceway that serves a building or structure. This requirement stems from the National Electrical Code, specifically addressing situations where electrical power is extended from a building to a remote structure, such as a post-mounted outlet along a sidewalk. In the described scenario involving 430-amp, 208-volt, single-phase circuits running in a single PVC raceway for 150 feet to feed 4 NEC 6.30R outlets mounted on a wood post, a grounding electrode system is necessary at the post. The primary reason for this requirement is to establish a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This grounding system ensures that in the event of a fault, such as a short circuit from a hot conductor to the grounded metal parts of the post or outlet boxes, the fault current will quickly trip the breaker, minimizing the risk of electrical shock or fire. The specific type and installation of the grounding electrode system must comply with Article 250 of the National Electrical Code. Several options are available for grounding electrodes, and this selection depends on site conditions and local code requirements. Firstly, a ground rod is a common choice, typically consisting of an 8-foot-long copper or copper-clad steel rod driven into the earth. The code requires a minimum length of 8 feet for ground rods and specifies the material and diameter. When driving a ground rod, it must be installed so that at least 8 feet of its length is in contact with the soil. If rock bottom is encountered, the rod can be buried horizontally in a trench that is at least 30 inches deep. Secondly, a ground plate is another option, consisting of a metal plate buried in the ground. The plate must have a surface area of at least 2 square feet and be made of iron or steel that is at least 0.25 inches thick, or of non-ferrous metal that is at least 0.6 inches thick. Thirdly, a concrete encased electrode, also known as a UFA ground, is a grounding electrode encased within a concrete foundation or footing. This type of electrode must consist of at least 20 feet of bare copper conductor not smaller than 4 American wire gauge encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. Fourthly, a ground ring encircling this structure can be used, consisting of a bare copper conductor not smaller than 2 American wire gauge buried at least 30 inches deep. In many jurisdictions, a combination of these electrodes is required to create a more robust grounding system. For example, 2 ground rods spaced at least 6 feet apart are often used. The connection to the grounding electrode must be made with a suitable grounding electrode conductor. The size of this conductor is determined by Table 250.66 of the National Electrical Code, based on the size of the ungrounded service entrance conductors. In this case, since the circuits are fed from a panel in the building, the grounding electrode conductor would be sized according to the size of the conductors feeding that panel. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed lugs, or pressure connectors. The connection must be accessible for inspection and testing. In addition to the grounding electrode system, an equipment grounding conductor must be run with the circuit conductors inside the PVC raceway. This equipment grounding conductor provides a low impedance path for fault current back to the source in the event of a fault. The size of the equipment grounding conductor is determined by Table 250.122 of the National Electrical Code, based on the size of the overcurrent protective device protecting the circuit. In this case, with 30-amp circuits, the equipment grounding conductor must be at least 10 American wire gauge copper or 8 American wire gauge aluminum. The equipment grounding conductor must be connected to the grounding terminals of the NEC 6.30R outlets and the wood post, as well as to any metal enclosures or boxes. The purpose of the equipment grounding conductor is to provide a safe path for fault current to flow back to the source, tripping the breaker and minimizing the risk of electrical shock. The National Electrical Code also addresses the bonding of metal parts to ensure electrical continuity and minimize voltage differences. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. All metal parts that are likely to become energized must be bonded together and connected to the equipment grounding conductor. This includes metal enclosures, boxes, and any other metal parts that could come into contact with a hot conductor. The bonding connections must be made with listed connectors or by exothermic welding. The purpose of bonding is to create a low impedance path for fault current, which helps to quickly trip the breaker in the event of a fault. In the scenario described, the wood post itself is not conductive and does not require bonding. However, any metal parts mounted on the post, such as the outlet boxes, must be bonded together and connected to the equipment grounding conductor. This ensures that if a fault occurs, the fault current will have a low impedance path back to the source, tripping the breaker and minimizing the risk of electrical shock. The installation of a grounding electrode system at the remote post also provides additional benefits, such as reducing ground potential rise during fault conditions and improving the overall stability of the electrical system. Ground potential rise is the increase in voltage potential in the earth surrounding a grounding electrode during a fault. By installing a grounding electrode system at the remote post, the ground potential rise is minimized, reducing the risk of electrical shock to people or animals that may be in the vicinity. Furthermore, the grounding electrode system helps to stabilize the voltage of the electrical system, reducing voltage fluctuations and improving the performance of sensitive electronic equipment. In summary, the National Electrical Code requires a grounding electrode system to be installed for any raceway that serves a building or structure, including the scenario described with the 430 amp, 208 volt, single-phase circuits running in PVC conduit to a wood post mounted along a sidewalk. The grounding electrode system must comply with Article 250 of the National Electrical Code, and the equipment grounding conductor must comply with Table 250.122. The installation of a grounding electrode system ensures electrical safety, minimizes the risk of electrical shock or fire, and improves the overall stability of the electrical system. It is also important to consider local amendments or interpretations of the National Electrical Code, as these can vary from one jurisdiction to another. Always consult with a qualified electrical inspector or engineer to ensure that the installation complies with all applicable codes and regulations. It's important to highlight some common mistakes to avoid during grounding electrode system installations. Firstly, neglecting to install a grounding electrode system at all is a serious violation of the National Electrical Code and can create a significant safety hazard. Secondly, using undersized grounding electrode conductors can limit the effectiveness of the grounding system and prevent other current protective devices from operating properly. Thirdly, improper connections to the grounding electrode can create high-resistance connections that impede the flow of fault current. Fourthly, failing to protect grounding electrodes from physical damage can compromise their effectiveness and reduce their lifespan. Fifthly, using dissimilar metals in the grounding system can lead to corrosion and reduce the effectiveness of the connections. By avoiding these common mistakes and following the requirements of the National Electrical Code, a safe and effective grounding electrode system can be installed, protecting people and property from the hazards of electrical shock and fire. Furthermore, regular inspection and testing of the grounding electrode system are essential to ensure its continued effectiveness. Grounding electrode systems can degrade over time due to corrosion, physical damage, or changes in soil conditions. Regular inspection can identify potential problems before they become serious hazards. Testing of the grounding electrode system can verify its effectiveness in providing a low impedance path for fault current. Several methods are available for testing grounding electrode systems, including the fall of potential method and the clamp on ground resistance tester. The fall of potential method involves injecting a test current into the grounding electrode and measuring the voltage drop between the electrode and a remote reference electrode. The clamp on ground resistance tester measures the resistance of the grounding electrode without disconnecting it from the system. Regular testing of the grounding electrode system can help to ensure that it is performing as intended and providing adequate protection against electrical hazards. In addition to the technical aspects of grounding electrode systems, it is also important to consider the human factors involved. Electrical safety training is essential for all personnel who work on or near electrical equipment. Training should cover the hazards of electricity, the proper use of personal protective equipment, and the procedures for working safely on electrical systems. Furthermore, it is important to promote a culture of safety in the workplace, where employees are encouraged to report potential hazards and to follow safe work practices. By combining technical expertise with a strong commitment to safety, the risk of electrical accidents can be significantly reduced. The information provided here is for general guidance only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrical engineer or inspector before designing or installing an electrical system. The National Electrical Code is a complex and constantly evolving document, and it is essential to stay up to date on the latest requirements. By following the requirements of the National Electrical Code and consulting with qualified professionals, a safe and reliable electrical system can be created. Remember that electricity can be dangerous, and it is always better to err on the side of safety. Take the time to learn about electrical safety and follow safe work practices. By doing so, you can protect yourself and others from the hazards of electricity. In a specific case of the 430 amp, 208 volt circuits feeding the NEC 6.30R receptacles, it's crucial to select appropriately sized conductors for the load. The National Electrical Code dictates ampacity requirements based on the continuous load and ambient temperature. Furthermore, voltage drop calculations should be performed to ensure that the voltage at the receptacles remains within acceptable limits, especially considering the 150-foot run. Voltage drop can significantly affect the performance of equipment connected to the receptacles, and excessive voltage drop can even damage equipment. The choice of PVC conduit for the raceway is suitable for underground and outdoor installations, but it's essential to ensure that the conduit is properly installed and supported. The National Electrical Code specifies requirements for conduit fill, support spacing, and burial depth. These requirements are designed to protect the conductors from physical damage and ensure the long-term reliability of the installation. When selecting the NEC 6.30R receptacles, it's important to choose receptacles that are rated for outdoor use and are suitable for the environmental conditions. Weather-resistant receptacles are designed to withstand exposure to rain, snow, and sunlight. Furthermore, the receptacle should be installed in weatherproof boxes to provide additional protection from the element. The wood post itself should be treated to prevent rot and decay, especially if it is in direct contact with the ground. Pressure-treated lumber is a common choice for outdoor posts, as it is resistant to moisture and insects. The post should also be securely mounted to provide a stable platform for the receptacles. In addition to the grounding electrode system and equipment grounding conductor, surge protection should also be considered. Surges can damage sensitive electronic equipment connected to the receptacles, and surge protection devices can help to protect against these surges. Surge protection devices should be installed at the panel under the receptacles to provide comprehensive surge protection. Proper labeling of the circuits is also essential. Each circuit should be clearly labeled at the panel and at the receptacles, indicating the voltage, amperage, and purpose of the circuit. This helps to prevent accidental overloading of the circuits and makes it easier to troubleshoot problems. Finally, it's important to document the installation thoroughly. A detailed wiring diagram should be created, showing the location of all conductors, devices, and grounding electrodes. This diagram can be invaluable for future maintenance and troubleshooting. By following these guidelines and paying attention to detail, a safe and reliable electrical installation can be created for the 430 amp, 208 volt circuits feeding the NEC 6.30R receptacles. Remember that electrical work can be dangerous, and it's always better to consult with a qualified electrician or engineer before undertaking any electrical project. The use of appropriate personal protective equipment, such as insulated gloves and safety glasses, is also essential when working on electrical systems. Always de-energize the circuit before working on it, and verify that it is de-energized using a voltage tester. By following these safety precautions, you can protect yourself from the hazards of electricity. The requirements of the National Electrical Code, along with any local codes or regulations, should be adhered to strictly.